Good morning, students. It's Monday, March 23rd. We got 1 week in to this online learning. We'll see how it keeps going. As always, you have questions, please contact me. Email, through Google Classroom, call school. I've been at school every day. Get a hold of me, let me know what your issues are. If you know of classmates who are having issues and maybe they're not seeing these videos, please let me know on behalf of those classmates what's going on, and so that I make sure I reach out to them. All right, so here's our learning targets for today. Your lesson has 2 parts. One, we're going to watch a video that I want you to take some notes on. 2, I have a video about how to do a project, and you'll have a link to that assignment in Google Classroom also. So the learning targets for this note section is that you can list and explain how each of these give us clues about the interior of the Earth. Okay, so on a test question, if I say, hey, give me 2 pieces of evidence for how we know about the interior Earth. Say, well, hey, we've got seismic information, or we do computer modeling, or we do density measurements of the Earth, composition of meteorites. What we're going to see is that these first 2 are the biggies, and these 2, I think, are things that you can understand, at least in a broad sense, how they give us some clues. This is kind of the same page. How do we know about the interior of the Earth? The biggies are the information that we get about seismic waves and computer modeling. Down here I have density of the Earth, meteorites. We get magma and lava samples that sometimes come up out of the Earth, but even those, they're only a little bit under the surface. They don't really tell us about the core of the Earth. The fact that Earth has a magnetic field, that suggests that there's something going on in the Earth, and that's another clue that we could have. So this might seem like a little bit of a sidetrack, but during the Cold War, 1950s and 1960s, we wanted to know what the Soviets were doing, because the United States was building and testing nuclear weapons, and we knew that the Soviet Union was building and testing nuclear weapons, and we wanted to keep an eye on them. And so from that, we built a network of seismic detectors all around the world. And so those seismic detectors were basically a way of trying to keep tabs on the Soviets at the time. But for our understanding of the Earth, they had this byproduct of giving us information that we had never had about the Earth before. So I'm using that word seismic, and if I use a word, we need to define it. So seismic relates to earthquakes and other vibrations in the Earth. There's shakings or vibrating that happens in the Earth. And there's different types of seismic waves. There's some that are called P waves. Those are, P stands for primary waves. We have S waves, which are secondary waves. And it has to do with the directions that the Earth is moving. P waves travel faster than S waves. That's something to note. P waves generally about 4 miles per second. S waves about half that speed. It does depend on the material that the waves are traveling through. Something else that's worth noting, though, is that S waves cannot travel through liquids. Okay, the energy just doesn't transfer properly through liquids, whereas P waves can travel through liquids. That's going to be significant. There are other types of seismic waves. There are surface waves and things like that. We're going to focus in on these 2, P waves and S waves. So let's imagine that here's the surface of the Earth, And around the Earth, we have seismic detectors. So I don't know what a seismic detector exactly looks like, but I made some little symbol and I put them around the surface Earth. These are all seismic detectors. And let's say an earthquake happens right there. And that earthquake sends out energy and it travels in the form of waves. And those waves travel to each of these seismic stations. So the wave is going to travel from there to there. It's going to travel from there to there, there to there. And I'm just going to take the time to draw my waves going to each of these seismic stations. That one didn't want to link up very good. Now, what can we see from this? You can see that the distance from the earthquake to this station is longer. You can see the distance from the earthquake to this station is a lot shorter. So hopefully it makes sense to everybody that the further the distance away, the longer the time is before the wave energy gets to that station. So this station's going to know about the earthquake first, and this quake's going to be a little bit later, and this station's going to be a little bit later and a little bit later. Well, when scientists take that information and they make a chart, we know our distance, and we're looking at the time versus distance. And we start measuring the time. So the time to this station, the time to this station, time to the next one. And well, what they found was the graph, and this isn't quite right. I can do better. Distance, time. So let's say the times were coming up like this, and then go kind of like that. And what they noticed on this was that these times kind of line up, and these times kind of line up, but there's something changes. And so that leads to questions. Why were there changes in the speed of these waves? Because the distance and time is related to speed. It's related to the speed of the wave. Well, there we go. Some scientists suggest, well, maybe the Earth is different as we go deeper. So these waves up here just travel through the surface of the Earth, but some of these waves have to travel through deeper parts of the Earth, and maybe that has different composition, and the waves travel at a different speed in a different material, and that's what's affecting our graph. And so we're getting ideas from seismic information that, oh, there's different structure within the Earth. And in fact, if you look at, at what distance does this change take place, we start getting ideas for how deep those layers must be. Now, it's pretty complicated stuff, but what can you do as freshmen in high school? Well, hopefully you can look at this and say, oh yeah, I see that those waves had to travel through a deeper part of the Earth. If that's made of different material, I can understand that they would travel at different speed. Flip that over and say, oh, because the waves are traveling at different speed, there must be a different material in the Earth. So here's a diagram. This is what a seismogram might look like. So basically imagine a roll of paper, and as the paper is going underneath a pen, and when the vibration gets to the station, the pen vibrates. And I think you've probably seen that in movies and TV shows and things like that. So there's always just a little background noise, nothing much is happening, and the earthquake arrives, and we get this shaking. The first earthquake to arrive is a P wave. The second earthquake to arrive is an S wave, and then later come the surface waves. We're not going to worry about those. And if you look at this, if I just pay attention to the P waves, you see that the P waves start out moving like this, and then that line kind of, the slope of the line changes a little bit. Here's the S waves, starts out steeper, and then the slope changes. that's what I was talking about on the last page. But now, if you look at the difference between the P waves and the S waves, all right, we can take this, and by looking at the time difference between the two, we compare it to this graph, and we can actually get distance. So this is how scientists figure out where an earthquake happened, is by looking at the difference between the P wave time and the S wave time. Here's a diagram that's been put together relative to the Earth. And so this is, imagine that an earthquake happened up here, and we've got these seismic stations all around the Earth detecting the waves. And the way the waves appear to move through the Earth appears to get denser as you go deeper, and so the waves travel a little bit different speed, and that's what lends itself to some of these curved paths. But then you get to places where you see that over here, there's no waves getting to this part. And so we try to explain, how can there be no waves getting here? And so scientists propose that, oh, there must be a layer in here that when the wave hits that, it bends. Some of you wear glasses, contact lenses. I think you all are at least a little bit aware that light bends when it goes through glass. Light bends when it goes through different objects. If you look at an aquarium with fish in it, you sometimes, if you're looking at an angle at it, you can see the fish in two different spots, and you know it's the same fish. The light's being bent by when it goes from the water of the aquarium to the air. These waves are getting bent when it goes through different material. And so by looking at where the waves get to and where they don't, we get clues about what's inside. So the single biggest piece of information that we have about what's in our Earth is seismic information. Okay? That's a critical one for you to know. So, next up, computer modeling. And what can I say about computer modeling? I can't show you much. The computer modeling goes hand in hand with the seismic information. So from the seismic information, we get an idea what we think the Earth might be like. And we build a computer model. And we say, all right, what if this happened? And we run our computer model to see what results it gives us. And then we look at the model and say, does that match what we actually see in the real world? If it doesn't, we need to fix our computer model. If it does, all right, our model's on the right track. But when we run it, maybe there's some details that just aren't quite right. So we tweak the computer model a little bit and we run it again. And we keep designing this model based on everything that we learn and ideas that we get. We build that model that simulates the Earth. Now, I think you guys probably should be able to understand this better than most people. A lot of you like to play games. And what are those games other than a model of what happens in our world? A lot of times. Some of those games, now I don't like to play the games where you go around just shooting things, but think about some of the games that I bet some of you have seen. How about Cut the Rope? You got little Om-Nom in there, you got to feed him some candy, and you know, you start things, the candy swinging maybe back and forth, you cut the rope and it swings in a certain way, and that computer game is modeling the way real life works, our world works. There's gravity pulling down, the rope is going to pull sideways. If you cut the rope, it's going to travel in a trajectory. That's a computer model. Okay, so what we do is we take our information that we know about the Earth, we develop a computer model, and we test it, and then sometimes the model tells us or suggests things that we maybe haven't thought of before. And it helps us to understand later. Now, if the model is making accurate predictions of things that we see, we might also guess that the model's maybe giving some reasonably accurate predictions of things we haven't seen yet. Density of the Earth. This is going to be in our lesser category. The two main ones are seismic waves and computer modeling. A couple hundred years ago, a guy by the name of Isaac Newton Hopefully you've heard of him before. He did some measurements and calculations about the Earth. And he found that if you take the overall mass and volume of the Earth and calculate its density, you end up with a value that's about twice the density of the rocks that we find around us. And that's weird, okay? So this has a density. The rocks that we have here have a density, but this density is twice as big as this density. Now, it's the same Earth. How can that be? And so Newton suggested that there must be material in the Earth that's much more dense than what we find on the surface. So by doing density calculations, we're saying there's got to be something in here that we don't know. I think of it, if I had a room and there's people in that room, and I told you that the average weight of people in that room was 150 pounds. And out of the room walks a person, and we find his weight is 100 pounds. Another person walks out, they're 100 pounds. Another person walks out, they're 100 pounds. Another person walks out, and they're 100 pounds. At some point, you got to realize that, hey, there must be some people in this room that are way over 100 pounds, or the average could never be 150, because the average is always in between the lowest and highest values. So if there's some people walking out that are 100 pounders, there's got to be some people in there maybe like me that are way over that rate to bring the average up. If what we measure here on the surface of the Earth is usually about a density of about 2.7 to 2.9 grams per cubic centimeter. But when we do math for the entire Earth, we come up with a value more like about 5.5. And I'm saying Newton did his calculations a couple hundred years ago. Today, we have better information, better measurements, and we still get a value that's close to twice the density. The Earth as a whole has twice the density of our surface rocks, which means there has to be something more dense somewhere inside the Earth that we can't see. Okay, one more. Meteorites. So here's our Earth, and sometimes a piece of rock crashes on Earth, okay? It's a meteoroid when it's out in space. It's a meteor when it's burning up through our atmosphere. Sometimes they're big enough that they don't entirely burn up and a piece of rock hits the Earth. Now, some of those meteorites that hit the Earth are rocky, and they have a composition very similar to the rocks that we see on the surface of the Earth. That makes sense, doesn't it? But some of those meteors are made almost entirely of metal. And that's weird, because we have rocks that contain bits of metal in them, but for the most part, on the surface of the Earth, we don't find just lumps of metal. And we think that these meteorites, this stuff out in space, formed in the same cloud, the solar system, the Earth formed from the same material that formed that material. So if there are pieces of nearly pure metal out there in space, shouldn't some of that metal be in the Earth? And we don't see it. So if we don't see it, it must be someplace we don't see, which is inside the Earth. All of these things together add up to say, hey, there's something heavy and dense in the Earth. There's metal in the Earth. Metals are a lot more dense than the rocks that we see around us. The seismic waves don't travel through some parts of the Earth very well. It all suggests to give us some clues about what's in our Earth. So, there's your video today. We're talking about how do we have evidence, how do we know about what's in our Earth. You might wonder, and I'll finish with this. You might say, well, why don't we just dig a hole and see? I believe, I'd have to look it up. There was a hole that was drilled in Russia, and I think they made it down, I want to say it was about 7 miles that they made it. That's the deepest hole that's ever been drilled on the surface of the earth. 7 miles. This earth is about 4,000 miles in radius. So when we go 7 miles, let's say 4,000 miles, 10% is 400 miles, 1% is 40 miles, 0.1% is 4 miles. So the deepest hole we've ever drilled is less than 0.2% of the radius of the earth. And that project was very costly and eventually had to be abandoned because it's just, the technology isn't there to drill into the deeper earth. So can we make a hole and look inside? No, we can't. We have to find our information from other things. All right, so you should have taken some notes on structure of the earth, or how we know about the structure of the earth. And now you have a video showing you how to do a project. That's what you need to work on. The project I want by Wednesday. By Wednesday. Wednesday is the last day of the quarter. I need to get that in. I'm going to include that as one last grade for your quarter. All right. Stay safe out there. Hope to see your faces soon. Take care of yourselves. Bye-bye.